When we say that light does not travel in a simple straight line way as we imagine, we are confronting one of the deepest gaps between human intuition and physical reality. From everyday experience, straight lines feel natural. We throw a stone, we watch it arc. We shine a torch, and the beam appears to cut cleanly through the air. Our brains are built to understand motion in terms of objects following clear paths from one place to another. For centuries, this intuition shaped how people thought about light. It was imagined as tiny particles flying forward or as waves rippling smoothly through space. Both ideas still tied to the comfort of a single, well-defined path. What Feynman showed is that this picture, while useful at large scales, collapses completely when examined closely. At the most fundamental level, light refuses to commit to a single route. It behaves as if the concept of the path does not exist in the way we think it does. Instead of traveling along one neat line, light behaves as though it spreads its influence across all possible routes between its starting point and its destination. These routes include the obvious straight line, but also infinitely many others that twist, curve, loop back, or wander erratically through space. This is not poetic exaggeration. It is a precise statement supported by quantum theory and experimental evidence. The strangeness lies not in the mathematics, but in how violently it contradicts common sense. To understand why our intuition fails here, we need to recognize that human intuition evolved in a world where quantum effects average out. We never see single photons with our naked eyes. We see billions of them at once, behaving collectively in ways that hide their underlying complexity. When many photons move together, their strange behaviors blend into something that looks orderly and predictable. Straight lines emerge not because light truly follows a straight path, but because all other possibilities cancel each other out at large scales. The straight line is an illusion created by overwhelming numbers. Feynman approached this problem by stripping away unnecessary assumptions. Instead of asking what path light takes, he asked how likely different outcomes are. In quantum mechanics, the fundamental quantity is not position or trajectory, but probability amplitude. Light does not move like a tiny bullet that occupies a single position at each moment. It exists as a spread of possibilities, each carrying a certain weight. These possibilities interfere with one another, strengthening some outcomes and erasing others. The path we observe is simply the one that survives this interference. This is why the idea of a single straight line is misleading. It assumes that nature chooses a route in advance. In reality, there is no evidence that such a choice is ever made. Instead, all possibilities are allowed, and the final result emerges from their interaction. When light travels through empty space, the straight line path dominates because nearby paths reinforce it, while wildly different paths cancel out. But this dominance is not absolute. Under the right conditions, such as when light passes through narrow slits or around edges, the contributions of non-straight paths become visible. Diffraction and interference patterns are direct evidence that light does not simply go straight. Consider the famous double-slit experiment. When light passes through two narrow openings, it produces a pattern of bright and dark bands on a screen. This pattern cannot be explained if each photon travels along a single, definite path through one slit or the other. Instead, the pattern emerges as if each photon explores both slits and all possible paths beyond them. The interference pattern is not added later. It is built into the way light propagates. Even when photons are sent one at a time, the same pattern eventually forms, revealing that the behavior is not collective, but intrinsic. This is where Feynman's insight becomes unsettling. He emphasized that there is no underlying classical picture that explains what is really happening in familiar terms. Any attempt to imagine a photon choosing a route, splitting itself, or secretly coordinating with other photons leads to contradictions. The only consistent description is mathematical, and it tells us that the straight-line picture is a crude approximation. Reality, at its core, is not made of paths but of probabilities. The idea that light does not travel simply also reshapes how we understand space itself. In classical thinking, space is a passive stage on which events unfold. Objects move through it along trajectories, and light obediently follows geometric rules. Quantum theory overturns this view. Space becomes an active arena filled with possibilities. Light does not merely pass through space. It interacts with the structure of spacetime at every moment. The straightness we perceive is not imposed by space, but emerges from the way probabilities add up. This perspective also explains why light behaves differently in different environments. When light enters glass or water, it slows down. If light truly followed a single straight line, slowing down would simply mean moving more slowly along that line. But what we observe is bending, refraction, and sometimes even reflection. These effects make sense only if light is sensitive to the time it takes to travel, not just the distance. In denser media, paths that look longer in distance may actually take less time because of changes in speed. Light responds to this by favoring paths that minimize travel time, not distance. Once again, the straight line loses its privileged status. What makes this even more profound is that the same principle applies even in empty space. The straight path is not chosen because it is straight, but because nearby paths interfere constructively along it. If the laws of physics were slightly different, or if spacetime itself were curved in certain ways, the dominant path would change. Gravity, for example, bends light not by pulling it like a force, but by altering the geometry of spacetime. Light still follows the same quantum rules, but the landscape of possibilities is reshaped. Feynman often stressed that this is not a story about ignorance or hidden details waiting to be discovered. There is no secret classical explanation beneath the quantum one. The strangeness is not temporary. It is fundamental. The demand that light must really go somewhere in a definite way is a demand imposed by human psychology, not by nature. Physics progresses not by satisfying intuition, but by abandoning it when it fails. This realization has philosophical consequences. It challenges the idea that reality is built from well-defined objects moving along clear paths. Instead, it suggests that reality is built from interactions, probabilities, and constraints. Light does not travel as a thing with a trajectory. It propagates as a process. The straight line is a useful fiction, a statistical average that works when precision is not required. Yet, despite its strangeness, this view of light is astonishingly powerful. It predicts experimental outcomes with incredible accuracy. It explains why lasers work, why semiconductors function, and why modern communication technologies are possible. The same mathematics that denies the simplicity of straight-line motion also enables the most precise technologies humanity has ever built. This is not a failure of understanding. It is understanding at its deepest level. In everyday life, we will continue to draw straight rays of light in diagrams and teach children that light travels in straight lines. This is not wrong, but it is incomplete. Beneath that simplicity lies a richer and more unsettling truth. Light does not march forward along a single route. It spreads, explores, interferes, and only at the end do we see a clean result. What appears simple is born from complexity. Feynman's explanation invites us to rethink what it means to travel at all. Travel, in the quantum sense, is not about following a path, but about contributing to an outcome. Light does not need to know where it is going. It does not need instructions or intentions. It obeys rules that allow everything, and from that allowance, order emerges. The straight line we draw is not a command that nature follows. It is a summary of what survives. This is why something strange truly happens when light travels. The strangeness is not an odd exception or a clever trick. It is a reminder that the universe operates on principles far removed from everyday experience. Light reveals this more clearly than almost anything else because it sits at the intersection of space, time, and quantum reality. By abandoning the comforting image of straight line motion, we gain access to a deeper, more accurate picture of how the universe works, a picture that is less intuitive but far more honest. When we say that light explores all possible paths simultaneously, we are stepping directly into the heart of what makes quantum physics feel so unsettling. This statement does not mean that light is confused, indecisive, or magically aware of every route in advance. It means that the classical idea of motion itself breaks down at very small scales. In the quantum description, light does not behave like an object moving through space along a single continuous track. Instead, it behaves like a process that spreads across possibilities, allowing every conceivable path between 2 points to contribute to what finally happens. Richard Feynman explained this idea using a framework that feels almost shocking when first encountered. Instead of asking which path light takes, he asked how each possible path contributes to the final result. In this view, light behaves as if it travels along every imaginable route at once. Some of these routes are sensible and direct. Others are absurdly indirect, looping back on themselves or wandering far away before arriving. Even paths that seem completely unreasonable are included. Nature does not forbid them. What matters is not whether a path looks sensible to us, but how its contribution interacts with all the others. This is where simultaneity enters the picture, though it must be understood carefully. Light is not splitting into countless miniature copies, each physically racing along a different path. That image is tempting but misleading. What exists simultaneously are the possibilities, encoded mathematically as probability amplitudes. Each possible path contributes an amplitude with a certain magnitude and phase. These phases determine how the contributions combine. Some reinforce each other, while others cancel out. The final outcome we observe is the result of this vast interference process. To grasp why this matters, it helps to abandon the idea that nature must operate efficiently or economically in the way humans prefer. Classical physics assumes that systems follow optimal paths, minimizing effort or distance. Quantum physics does not impose such restrictions. It allows everything that is not forbidden. Light, therefore, does not choose a path in advance. It allows all paths to participate, and only afterward does a clear pattern emerge. This idea explains phenomena that would otherwise be impossible to understand. Interference patterns, diffraction, and quantum tunneling all rely on the fact that particles and light behave as if they explore multiple possibilities at once. In the case of light, interference is the most striking example. When light passes through narrow openings or around obstacles, it creates patterns of brightness and darkness that cannot be explained by straight line motion alone. These patterns arise because different paths interfere constructively in some regions and destructively in others. Where contributions reinforce, light appears bright. Where they cancel, darkness appears. What makes this even more remarkable is that this behavior persists even when light is emitted one photon at a time. There is no crowd of photons coordinating their behavior. Each individual photon behaves as if it has access to all possible paths. Over time, as many photons arrive, the interference pattern builds up. This shows that the exploration of paths is not a collective illusion, but a fundamental property of light itself. Feynman emphasized that this is not merely a metaphor. The mathematics of quantum electrodynamics, one of the most accurate theories ever developed, is built on this principle. Calculations involve summing contributions from all possible paths. There is no shortcut that selects a single trajectory. The universe, at its most fundamental level, seems to perform an enormous computation, considering every allowed history before producing an outcome. This raises a natural question: why do we not see chaos everywhere? If light truly explores all paths, why does the world appear orderly and predictable? The answer lies in interference. Most paths cancel each other out almost perfectly. Paths that differ wildly from one another tend to have phases that vary rapidly, causing their contributions to average to zero. Only families of similar paths, usually clustered around the path of least time, reinforce one another strongly enough to survive. The apparent simplicity of light's motion is therefore not fundamental. It is an emergent feature. This perspective changes how we think about causality. In classical physics, causes precede effects along well-defined trajectories. In the quantum picture, outcomes emerge from a network of possibilities rather than a single chain of events. Light reaching a detector is not the result of one path being taken, but of all paths conspiring to produce that detection. The cause is distributed across possibilities, not localized in a single history. The phrase "all possible paths" must also be understood in a precise sense. These paths are not limited to smooth, continuous curves. They include highly irregular paths that would never be followed by a classical object. At very small scales, space and time are not experienced smoothly. Quantum fluctuations dominate, and the notion of a smooth trajectory loses meaning. Light is sensitive to this structure, and its behavior reflects the underlying complexity of spacetime. This idea also helps explain why intuition fails so badly at the quantum level. Human intuition is shaped by macroscopic objects, where quantum interference averages out. When we throw a ball, it does not explore all possible paths because the probabilities for alternative paths cancel almost completely due to the object's mass and interactions with the environment. Light, being massless and weakly interacting, retains its quantum nature even at scales we can observe. It reveals features of reality that are normally hidden. Feynman often pointed out that there is no classical story lurking behind this behavior. There is no mechanism in which light secretly checks every path or rapidly moves back and forth. Any attempt to visualize such a mechanism leads to contradictions. The correct description is mathematical, and it resists translation into everyday imagery. This is not a failure of imagination, but a sign that reality is structured differently from our expectations. The exploration of all paths also sheds light on the role of boundaries and constraints. When light encounters an obstacle, such as a mirror or a barrier with a slit, the set of allowed paths changes. Some paths are blocked, others are redirected. The interference pattern changes accordingly. Reflection and refraction emerge naturally from this process. They are not special rules imposed on light, but consequences of how possibilities are restricted and combined. This framework also connects deeply with the principle that light follows the path of least time. In the classical limit, where many nearby paths reinforce each other, the dominant contribution comes from paths that make the travel time stationary. This is why light appears to obey simple geometric laws in mirrors and lenses. These laws are not fundamental instructions. They are summaries of what happens when interference is taken into account. Beneath them lies the richer picture of all paths contributing. One of the most profound implications of this idea is that the universe is not economical in the way we expect. It does not compute only what is necessary. It allows everything, and from that allowance, structure emerges. This challenges the idea that nature is fundamentally deterministic in a classical sense. Outcomes are predictable only in terms of probabilities, not certainties. Light reaching a particular point is not guaranteed by a single history, but by the statistical dominance of certain contributions. This view also reframes the meaning of simultaneity. When we say that light explores all paths at once, we are not referring to time in the ordinary sense. We are describing a timeless calculation in which all possibilities are included. Time enters only when we observe outcomes. Before that, the description is not one of events unfolding, but of contributions being summed. This is why attempts to imagine the process unfolding in time often lead to confusion. Feynman was clear that this strangeness is not optional. One cannot accept the experimental results of quantum physics while rejecting this underlying principle. The success of modern physics rests on it. Technologies that rely on interference, such as lasers, fiber optics, and quantum sensors, work precisely because light behaves in this counterintuitive way. The exploration of all paths is not philosophical speculation. It is an experimentally verified feature of the world. This idea also carries a quiet philosophical message. It suggests that reality is less about objects doing things and more about relationships between possibilities. Light does not act. It participates. It contributes. What we observe is not the motion of a thing, but the outcome of an interaction shaped by countless invisible alternatives. This shifts the focus of physics from objects to processes. In accepting this, we are forced to give up the demand for a simple picture. Feynman often said that nobody truly understands quantum mechanics in the classical sense. What we can do is learn how it behaves and accept that its behavior does not need to align with everyday logic. Light's exploration of all possible paths is not meant to be visualized in a comfortable way. It is meant to be calculated and tested. In the end, this keynote reveals why light is such a powerful guide to the nature of reality. By refusing to follow a single path, light exposes the hidden structure beneath the world we see. It shows that what appears simple is built from complexity, and what appears definite is born from uncertainty. When light travels, it does not merely move from here to there. It participates in a vast, invisible conversation among all that could happen, and from that conversation, the universe produces a single, observable result. When we say that time, not distance, decides the path light actually takes, we are stepping into a principle that quietly reshapes how reality operates. Our everyday thinking treats distance as the main measure of a journey. The shortest route feels like the obvious choice, whether we are walking across a room or driving through a city. For centuries, it seemed natural to assume that light must behave the same way, traveling along the shortest geometric line between 2 points. What Feynman emphasized is that this assumption is not just slightly wrong, it misses the real rule entirely. Light does not care about distance in the way we do. It responds to time. This idea did not begin with quantum mechanics. Long before Feynman, scientists noticed something peculiar about how light reflects and refracts. When light bounces off a mirror, the angle at which it arrives matches the angle at which it leaves. When it passes from air into water or glass, it bends in a precise and predictable way. These rules can be derived by assuming that light follows the path that takes the least time, not the shortest distance. This principle, known as the principle of least time, appears simple on the surface, but its implications are profound. To understand why time dominates, we need to recognize that light does not move at the same speed everywhere. In a vacuum, it travels at its maximum speed. In materials like water or glass, it slows down. This means that a longer path through a faster medium can take less time than a shorter path through a slower one. Light adjusts accordingly, bending its path to minimize the total travel time. What looks like an intelligent choice is actually an emergent result of deeper physical laws. Feynman took this classical principle and showed that it emerges naturally from the quantum behavior of light. In the quantum picture, all possible paths contribute, but the paths that make the travel time stationary dominate. Paths close to this special timing reinforce each other through constructive interference. Paths with significantly different travel times tend to cancel out. The result is that light appears to follow a single, well-defined route, even though it never truly commits to one. This explains why distance alone is not the deciding factor. A path that is slightly longer in distance but similar in time can still contribute strongly. A path that is short but significantly slower will not. Time, not geometry, governs which possibilities survive. The straight line we draw in diagrams is therefore a summary of what remains after interference, not a fundamental instruction. This perspective also reveals why light behaves so predictably in optical systems. Lenses, mirrors, and prisms work because they shape the timing of different paths. By changing how long light takes to travel through various regions, these devices control which paths reinforce and which cancel. Focusing, magnification, and image formation are not the result of light obediently following geometric rules, but of interference favoring certain timing relationships. The dominance of time also connects deeply with relativity. According to Einstein's theory, time and space are not separate entities, but parts of a single structure called spacetime. The speed of light links them together. Light always travels along paths that make its spacetime interval zero. In curved spacetime, such as near massive objects, these paths bend. Light does not feel a force pulling it sideways. Instead, the geometry of spacetime alters the timing of possible routes. Once again, time determines the outcome. From this point of view, gravity's effect on light becomes less mysterious. When light passes near a massive object, its path curves. Classical intuition might imagine gravity tugging on light like a string. Feynman's approach, consistent with relativity, shows that the curvature arises because spacetime itself is warped. The timing of different paths changes, and the paths that minimize or stabilize travel time are no longer straight in the ordinary sense. Light simply follows the rules it always follows, but the landscape has changed. The emphasis on time also reshapes how we think about causality. In everyday life, we imagine causes propagating through space along shortest routes. In physics, especially at relativistic and quantum scales, causes propagate according to time constraints. Signals cannot travel faster than light, because doing so would disrupt the causal structure of spacetime. Time ordering, not spatial separation, preserves the consistency of events. Feynman often highlighted that this principle does not imply purpose or foresight. Light does not know where it is going or calculate travel times in advance. The appearance of optimization arises from interference. The universe does not solve problems the way humans do. It allows everything, and the rules of interference ensure that only certain outcomes persist. The least time path is not chosen, it survives. This distinction matters because it removes the temptation to anthropomorphize nature. The laws of physics do not involve intention or efficiency. They involve consistency. Time enters as a fundamental constraint, shaping what can happen without requiring any decision-making process. The elegance of light's behavior comes from this simplicity, not from hidden complexity. The idea that time governs motion also has consequences beyond optics. In quantum field theory, particles propagate according to similar principles. All possible histories contribute, but those that satisfy certain timing conditions dominate. The same mathematical structures that describe light also describe electrons, quarks, and other fundamental entities. Light is not an exception, it is a clear example of a general rule. At a deeper level, this suggests that time is not merely a background parameter, but an active ingredient in physical law. The way time accumulates along a path determines whether that path matters. This challenges the intuitive picture of time as something that simply flows independently of events. Instead, time is intertwined with motion and interaction. Feynman's explanations made this abstract idea tangible by connecting it to observable phenomena. Reflection, refraction, focusing, and even mirages can all be understood through the lens of timing. When light bends near a hot surface, it is responding to changes in air density that alter its speed. The shimmering effect is not an illusion, but a visible consequence of time-based path selection. This also explains why optical illusions and distortions are so sensitive to environmental conditions. Small changes in temperature, pressure, or composition can alter travel times enough to change which paths dominate. Light is exquisitely sensitive to timing, and this sensitivity reveals the underlying structure of the medium it travels through. Perhaps the most striking implication of this keynote is how it reframes simplicity. What appears to be a simple straight line motion is actually the result of a delicate balance of possibilities. The straight path is not privileged by geometry, but by timing. If time were altered, the path would change. This means that the laws governing light are deeply relational. They depend on how light interacts with its environment, not on absolute rules imposed from outside. Feynman's insight invites us to let go of the idea that nature must operate in the most obvious way. The universe is not designed to be easily understood. It is designed to be consistent. When we accept that time, not distance, governs light's behavior, we gain a framework that unifies optics, quantum mechanics, and relativity. What once seemed like separate phenomena become expressions of the same underlying principle. In the end, this keynote reveals that light is a messenger of time. Its path records the timing constraints of the universe. By studying how light moves, bends, and arrives, we are not just learning about illumination or vision. We are learning about the structure of reality itself, a structure in which time quietly but decisively shapes everything that can happen. When we say that reflection and refraction emerge from probability rather than intention, we are removing one of the most deeply rooted misconceptions in how people imagine light behaving. In everyday language, we often speak as if light decides, to bounce off a mirror or chooses, to bend when entering water or glass. These phrases are convenient, but they quietly smuggle in a false picture, the idea that light is a tiny object following rules as if it understands geometry. Richard Feynman's explanation strips away this illusion and replaces it with something far more subtle and far more powerful. Reflection and refraction are not instructions that light follows. They are outcomes that emerge from probability and interference. To appreciate this, we need to let go of the idea that light knows what a mirror is or recognizes the boundary between air and glass. At the fundamental level, light interacts with charged particles, primarily electrons, in the material it encounters. These interactions are governed by quantum electrodynamics, a theory that does not contain any rule saying bounce here or bend there. Instead, it describes probabilities of interaction, delays in response, and the way emitted and absorbed photons interfere with one another. The familiar laws of reflection and refraction are not written into the universe as commands. They appear when countless microscopic interactions combine. Feynman emphasized that when a photon approaches a surface, there is no single, clean event taking place. The photon does not arrive at one precise point, bounce, and depart. Instead, there is a spread of possible interaction points across the surface. Each point contributes a tiny probability amplitude. These amplitudes have phases that depend on the timing of the interaction. When all these contributions are added together, most of them cancel out. Only a narrow range of possibilities survive, and these surviving possibilities correspond exactly to the angles of reflection and refraction we observe. This is a crucial shift in perspective. The mirror does not enforce the law of reflection. The law of reflection is a statistical result. It is the angle at which the contributions from many possible interaction points reinforce one another instead of canceling out. At other angles, destructive interference wipes out the signal. What remains looks like a sharp, well-defined beam, giving the illusion of a precise, intentional bounce. The same reasoning applies to refraction. When light enters a medium like glass, it interacts with atoms that absorb and re-emit the light. This process introduces tiny delays. The speed of light in the medium is reduced, not because photons are physically slowed down like cars in traffic, but because they spend time interacting with the material. These delays change the phase relationships between different paths. Once again, all possible paths contribute, but only those that satisfy certain timing conditions survive interference. The bending of light at the boundary emerges naturally from this process. What makes this explanation so powerful is that it unifies phenomena that once seemed separate. Reflection, refraction, diffraction, and scattering are not governed by different rules. They are all expressions of the same underlying principle: probability amplitudes interfering with one another. The surface of a mirror does not impose geometry, it shapes probabilities. The boundary between air and glass does not force light to bend, it alters timing. This view also explains why reflection and refraction are so precise. The angles involved are not approximate or fuzzy. They are sharp and reliable because interference is unforgiving. Small deviations in angle lead to large changes in phase, causing destructive interference. Only very specific conditions allow constructive interference to persist. Precision emerges not from control, but from cancellation. Feynman often pointed out that this probabilistic explanation is not an optional interpretation layered on top of classical laws. It is the foundation from which those laws arise. If one tries to remove probability and describe reflection and refraction purely in classical terms, one ends up with rules that work but have no deeper justification. Quantum theory provides that justification by showing how those rules emerge from more fundamental behavior. This perspective also dissolves the temptation to think of light as a rigid entity obeying commands. Light does not carry a rulebook. It responds to interactions. When it encounters matter, it interacts with electrons, and those interactions are governed by probabilities. The outcome is shaped by the collective effect of enormous numbers of interactions, not by a single decisive event. The idea that probability, rather than intention, governs these phenomena also explains why imperfections matter. A slightly rough surface scatters light in many directions. From a classical point of view, this seems like a failure of the reflection rule. From Feynman's perspective, it is exactly what should happen. Irregularities change the timing and phase relationships of contributions from different points. Constructive interference no longer favors a single direction, so light spreads out. Diffuse reflection is not a breakdown of the law. It is the law operating under different conditions. Similarly, variations in material density affect refraction. Gradual changes in density, such as those caused by temperature gradients in air, lead to smooth bending of light and optical illusions like mirages. Sharp boundaries produce sharp bending. The underlying mechanism is the same in all cases. Probability amplitudes add up differently depending on how timing varies across space. This probabilistic view also clarifies why light can sometimes behave in ways that feel paradoxical. Total internal reflection, for example, occurs when light inside a dense medium hits the boundary at a steep angle and does not emerge into the less dense medium. Classical explanations describe this as light being trapped or unable to escape. Feynman's explanation shows that this effect arises because there are no paths into the second medium that satisfy the necessary timing conditions for constructive interference. The probabilities cancel out completely. Reflection dominates not because light is confined, but because other outcomes are suppressed. Another striking implication of this view is that reflection and refraction are not perfectly clean at the microscopic level. There is always some probability of scattering, absorption, or transmission in unexpected directions. These probabilities are usually tiny, but they are never zero. The clean laws we learn are approximations that emerge when probabilities overwhelmingly favor certain outcomes. Nature does not deal in absolutes, it deals in likelihoods. This also explains why extremely precise experiments can detect deviations from classical behavior. At very small scales, or with very sensitive measurements, subtle effects become visible. These effects do not violate the classical laws. They reveal the probabilistic structure beneath them. What appears to be a strict rule is, in reality, a dominant trend. Feynman's approach forces us to rethink what a physical law actually is. A law is not a command issued to matter. It is a summary of what usually happens given the underlying probabilities. Reflection and refraction laws summarize the most likely outcomes of light interacting with matter. They are reliable because the probabilities are overwhelmingly skewed, not because the universe enforces obedience. This way of thinking also bridges the gap between classical and quantum physics. In classical optics, we draw rays and angles. In quantum optics, we sum amplitudes. The ray picture is not wrong, it is incomplete. It emerges from the quantum picture when probabilities align in a particular way. Understanding this relationship helps avoid the false choice between classical and quantum descriptions. One is a limit of the other. There is also a deeper philosophical shift embedded here. When intention is removed from the description of nature, what remains is structure. Reflection and refraction do not happen because light wants to follow rules. They happen because the structure of interactions makes some outcomes stable and others unstable. Stability arises from interference, not from purpose. This insight has practical consequences. Modern optical technologies rely on precise control of phase and probability. Anti-reflective coatings, for example, work by engineering interference so that reflections cancel out. Metamaterials bend light in unusual ways by manipulating how probability amplitudes add up. None of this would be possible if reflection and refraction were rigid commands. They are flexible because they are emergent. Feynman's explanation also helps us understand why learning physics often feels counterintuitive. We are trained to think in terms of causes and effects, intentions and responses. Quantum physics demands a different mindset. It asks us to think in terms of contributions and cancellations. Once this shift is made, many mysteries dissolve. Perhaps the most important lesson of this keynote is humility. The universe does not explain itself in terms that are naturally comfortable for human minds. Our language is full of intentions and choices because that is how we experience the world. Light, however, operates without such concepts. It follows no plan. It obeys no instructions. It participates in interactions governed by probability, and from those interactions, order emerges. Reflection and refraction, then, are not acts performed by light. They are patterns that appear when countless microscopic events are viewed from afar. They are shadows cast by probability on the screen of human perception. What looks like a simple bounce or bend is, in truth, the visible trace of an invisible statistical process. In accepting this, we gain a deeper appreciation for the elegance of physical law. Simplicity is not always fundamental. Often, it is the end result of complexity resolving itself through interference. Light teaches us this lesson every time it reflects from a mirror or refracts through glass. The miracle is not that it obeys simple laws, but that such simple laws emerge at all. When we say that light behaves like both a wave and a particle without contradiction, we are touching the point where language itself begins to fail. This idea has confused students, scientists, and philosophers for over a century, largely because the words wave and particle come loaded with expectations from everyday life. A particle is supposed to be a tiny object, localized at a point, following a path. A wave is supposed to be spread out, continuous, and capable of interference. In ordinary experience, these two ideas are mutually exclusive. Richard Feynman showed that the mistake lies not in light, but in our insistence that nature must fit neatly into human categories. Light does not switch between being a wave and being a particle depending on circumstances. It is not secretly one thing pretending to be another. It is something more fundamental that produces wave, like and particle, like effects when interacting with the world. The contradiction exists only if we demand that light conform to classical definitions. Once we abandon that demand, the paradox dissolves. The particle, like behavior of light, becomes evident when we observe how it is detected. Light arrives in discrete packets called photons. A detector does not register half a photon or a smear. Doubt fraction, it clicks or it does not. This discreteness is unavoidable. No matter how weak the light source, detections always occur as individual events. This is what led physicists to conclude that light carries energy in quantized amounts. In this sense, light undeniably behaves like a particle. At the same time, light produces interference patterns that cannot be explained by particles following single paths. When light passes through slits, reflects from thin films, or travels through optical devices, it shows patterns of reinforcement and cancellation. These are wave-like behaviors. They depend on phase, coherence, and superposition. No classical particle picture can reproduce these effects without adding artificial rules. The temptation is to imagine that light must secretly be either a wave or a particle, and that we simply lack the full picture. Feynman argued strongly against this idea. There is no hidden classical description waiting to be discovered. Quantum electrodynamics, the theory that describes light and its interaction with matter, does not contain waves or particles in the classical sense. It contains probability amplitudes. These amplitudes spread out like waves and produce localized events like particles. Both behaviors emerge naturally from the same mathematical structure. This is why there is no contradiction. The contradiction arises only if we assume that wave and particle are fundamental categories. They are not. They are approximations derived from everyday experience. Light does not belong to either category. It gives rise to phenomena that resemble both, depending on how we interact with it. Feynman emphasized that asking whether light is really a wave or a particle is the wrong question. It is like asking whether a melody is really a sequence of notes or a pattern of vibrations in air. Both descriptions are valid in their own contexts, but neither captures the full reality on its own. Light is described completely only by quantum theory, and quantum theory does not use classical metaphors as its foundation. The double-slit experiment reveals this most clearly. When light is sent through two slits and detected on a screen, it produces an interference pattern. This suggests wave-like behavior, but when the light is made extremely weak so that photons arrive one at a time, each photon still appears as a single localized spot on the screen. Over time, these spots build up the same interference pattern. Each photon contributes as a particle, but the distribution of impacts reflects wave-like interference. The same entity produces both effects simultaneously. There is no moment in this experiment where light decides to be one or the other. The experiment does not switch light's nature. It reveals different aspects of the same underlying behavior. The photon propagates as a spread of possibilities and interacts as a discrete event. These are not two modes of existence. They are two sides of one process. This understanding removes the need for mystical explanations. Light does not split into pieces, communicate with itself, or anticipate future measurements. It simply obeys quantum rules. These rules allow probability amplitudes to spread and interfere, and they require interactions to occur in discrete quanta. Nothing more is needed. Feynman often pointed out that this dual behavior is not unique to light. Electrons, protons, and even large molecules exhibit the same pattern when isolated from their environment. They produce interference like waves and detections like particles. Light is just the most familiar and dramatic example. The so-called wave-particle duality is not a special property of light. It is a universal feature of quantum objects. The reason we do not see this duality in everyday objects is not because it disappears, but because it is overwhelmed. Large objects interact constantly with their surroundings. These interactions destroy delicate interference effects. The probabilities collapse into well-defined outcomes so quickly that classical behavior dominates. Light, being massless and weakly interacting, retains its quantum character over long distances. making its dual nature visible. Feynman's explanation also clarifies why attempts to force a classical picture always fail. If we try to imagine a photon as a tiny ball, we cannot explain interference. If we try to imagine it as a classical wave, we cannot explain discrete detections. Any hybrid picture becomes inconsistent. Quantum theory avoids this by abandoning classical imagery at the fundamental level. It uses mathematics where such contradictions do not arise. This does not mean that understanding is lost. It means that understanding takes a different form. Instead of visualizing trajectories and shapes, we calculate amplitudes and probabilities. The predictions are precise, testable, and extraordinarily accurate. The discomfort comes not from confusion, but from the mismatch between theory and intuition. The wave-like aspect of light appears most clearly in how probabilities are distributed. The probability of detecting a photon at a particular location depends on the square of a wave-like amplitude. This amplitude spreads, interferes, and evolves smoothly. The particle-like aspect appears at the moment of interaction, when energy is transferred in a single, indivisible unit. Both aspects are essential. Remove either one, and the theory fails. This also explains why observation plays such a critical role. Measurement is an interaction. When light interacts strongly with a detector, the spread of possibilities resolves into a single outcome. This is not because consciousness intervenes, but because the quantum system becomes entangled with a macroscopic environment. The wave-like description applies between interactions. The particle-like description applies at interactions. There is no contradiction because they apply to different aspects of the same process. Feynman warned against thinking of this as light changing its nature when observed. Light does not behave one way when watched and another when ignored. The rules are always the same. What changes is the context of interaction. The language we use must change accordingly. This insight also reshapes how we think about reality itself. If light, one of the most fundamental entities in nature, cannot be neatly classified, then perhaps our categories are not as universal as we assume. The universe does not seem to be built from little objects moving through space like clockwork. It is built from interactions governed by probability. Objects and waves are emergent concepts, not fundamental ones. Feynman's approach was notable for its honesty. He did not pretend that this behavior could be made intuitive. He argued that the goal of physics is not comfort, but accuracy. Quantum electrodynamics works because it embraces the strange nature of light rather than trying to tame it. Its predictions match experiments to astonishing precision. That success is more important than satisfying our desire for familiar pictures. This keynote also carries an important lesson about learning. Many difficulties in understanding physics come from holding on too tightly to old metaphors. Once we accept that wave and particle are not ultimate descriptions, the confusion fades. Light stops being paradoxical and becomes consistent, though still strange. In practical terms, this dual behavior is not an abstract curiosity. It underlies modern technology. Lasers rely on the wave-like coherence of light. Photodetectors rely on its particle-like energy transfer. Quantum communication and computing exploit both aspects simultaneously. None of this would be possible if light were strictly one thing or the other. Perhaps the deepest insight here is that nature is under no obligation to align with human categories. Wave and particle are words we invented to describe limited experiences. Light transcends those limits. It forces us to expand our conceptual framework rather than squeezing reality into familiar boxes. In the end, the statement that light behaves like both a wave and a particle without contradiction is not a compromise. It is a rejection of a false choice. There is no need to decide what light really is. In classical terms, light is what quantum theory describes, and that description is complete on its own terms. The contradiction disappears once we stop demanding that the universe explain itself using the language of everyday life. When we say that the speed of light creates fundamental limits on reality, we are not merely talking about something moving very fast. We are talking about a boundary that shapes how the universe is allowed to function. This limit is not a technical inconvenience or a challenge for engineers to overcome. It is woven into the structure of space, time, causality, and even what it means for events to influence one another. Richard Feynman emphasized that the speed of light is not just a property of light itself. It is a property of reality. In everyday thinking, speed feels like a flexible quantity. Cars go faster than bicycles, planes go faster than cars, and it seems reasonable to imagine that with enough technology, anything could go arbitrarily fast. Classical physics encouraged this intuition. In Newton's universe, there was no ultimate speed limit. Objects could, in principle, move as fast as forces allowed. Time ticked the same everywhere, and space existed independently of motion. Light was just another thing moving through this backdrop. The discovery that light has a fixed maximum speed changed everything. Experiments showed that no matter how fast the source moves, light always travels at the same speed in a vacuum. This was not just surprising, it was revolutionary. It meant that speed was no longer relative in the way we expected. Something had to give, and what gave way were our assumptions about space and time. Einstein showed that the constancy of the speed of light forces space and time to adjust. Time slows down for moving objects. Lengths contract along the direction of motion. Events that appear simultaneous to one observer are not simultaneous to another. These effects are not illusions or measurement errors. They are real, measurable consequences of the light's speed limit. Feynman was careful to stress that these ideas are not philosophical speculations. They have been tested repeatedly and confirmed with extraordinary precision. The speed of light sets the maximum rate at which information can travel. This is crucial. Information is what allows causes to produce effects. If information could travel infinitely fast, causality would lose its meaning. Effects could occur before causes, depending on the observer. The universe would become logically inconsistent. The light speed limit prevents this. It protects the order of events. From this perspective, the speed of light is not about illumination or vision. It is about the integrity of cause and effect. When one event influences another, that influence cannot propagate faster than light. This creates a structure known as the light cone, which divides spacetime into regions that can affect one another and regions that cannot. Events outside each other's light cones are causally disconnected. No signal, no force, no information can link them. This has profound consequences for how we understand reality. It means that the universe is not a single, instantaneous whole where everything affects everything else at once. It is a network of local interactions, stitched together over time by signals that move no faster than light. What happens here cannot instantly change what happens far away. Distance matters not because of space alone, but because of time. Feynman often highlighted how strange this is from the perspective of common sense. We are used to thinking of the present moment as something shared across the universe. In reality, there is no universal now. Different observers moving differently slice spacetime into past, present, and future in different ways. The speed of light is what makes this unavoidable. If light were infinitely fast, everyone could agree on what is happening at the same time everywhere. Because it is not, simultaneity becomes relative. This challenges our intuitive picture of reality, but it also reveals a deeper consistency. The laws of physics look the same to all observers precisely because the speed of light is the same for all of them. This symmetry is not a coincidence. It is a fundamental feature of the universe. The light speed limit also explains why nothing with mass can reach or exceed the speed of light. As an object accelerates, its energy increases. Approaching the speed of light, the energy required to continue accelerating grows without bound. This is not because of mechanical resistance or friction. It is because the structure of spacetime itself resists such motion. Reaching the speed of light would require infinite energy, which is physically impossible. This limit is not a technological barrier waiting to be broken. It is not something future civilizations will overcome with better engines. It is a boundary embedded in the equations of physics. Any theory that allows faster than light travel must either violate causality or radically alter the structure of spacetime. Feynman was clear that while speculative ideas can be entertaining, they must be treated with caution because of these deep constraints. The speed of light also plays a central role in quantum physics. In quantum field theory, interactions are local. Fields influence one another only where they overlap in spacetime, and signals propagate at or below the speed of light. This ensures compatibility between quantum mechanics and relativity. Even quantum entanglement, often misunderstood as faster than light communication, does not violate this limit. While entangled particles exhibit correlations that appear instantaneous, no usable information is transmitted faster than light. The limit remains intact. Feynman emphasized that misunderstanding this point leads to confusion. Entanglement does not allow messages to be sent instantaneously. It reveals correlations, not causal influence. The speed of light still governs what can be used to send information or produce controlled effects. This distinction matters because it preserves the consistency of reality. If information could travel faster than light, paradoxes would arise. One could send messages into the past, create loops of cause and effect, and undermine the logical structure of physics. The light speed limit prevents this. It is a safeguard built into the universe. The limit also shapes our understanding of observation. When we look at distant stars, we are not seeing them as they are now, but as they were in the past. Light takes time to travel. The farther away an object is, the further back in time we see it. Astronomy is therefore a form of time travel into the past. This is not poetic language, it is literal. The speed of light ensures that information about distant events arrives delayed. This has a humbling effect. There are parts of the universe whose present state we cannot know, not because of insufficient technology, but because the information has not yet had time to reach us. There may be regions so distant that their light will never reach us at all. These regions are permanently beyond our observational horizon. The universe contains more than we can ever observe, not due to lack of curiosity, but due to the finite speed of light. Feynman often delighted in pointing out how deeply this limit influences even simple ideas. Consider simultaneity. Two explosions occurring far apart may seem simultaneous to one observer and sequential to another. There is no fact of the matter about which one really happened first unless they are causally connected. The speed of light defines what causal connection means. Without it, time ordering would be absolute. With it, time ordering becomes relative. This does not mean reality is subjective or arbitrary. It means that descriptions of reality depend on the observer's state of motion. The underlying laws remain the same. The speed of light ensures this consistency by forcing all observers to agree on its value, even if they disagree on measurements of space and time. The speed of light also acts as a bridge between energy and mass. Einstein's equation shows that mass is a form of energy scaled by the square of the speed of light. This enormous factor explains why small amounts of mass correspond to huge amounts of energy. Nuclear reactions, both in stars and in reactors, are governed by this relationship. The light's speed limit is therefore tied directly to the energy content of matter itself. From this point of view, the speed of light is not just a speed. It is a conversion factor linking space, time, energy, and mass. It appears throughout the fundamental equations of physics. Remove it, and the structure collapses. It is a cornerstone, not a detail. Feynman often encouraged people to resist the urge to think of these limits as frustrating. They are not constraints imposed on an otherwise unlimited universe. They are the rules that make the universe coherent. Without them, physics would not work. The predictability and stability we rely on would vanish. There is also a subtle philosophical implication here. The speed of light suggests that reality is not instantaneous. It unfolds. Events take time to influence one another. The universe is not a frozen block where everything happens at once. It is dynamic, with a built-in pace. This pace is not arbitrary. It is fixed by the deepest laws we know. The fact that light itself travels at this maximum speed is not an accident. Light is massless, and massless entities move at this ultimate speed. Anything slower is bound by mass and energy constraints. Light, therefore, marks the boundary between what is possible and what is not. Feynman's way of explaining this avoided mysticism. He did not present the speed of light as a cosmic commandment. He presented it as an observed fact with unavoidable consequences. Physics did not choose this limit. The universe revealed it, and physics adapted. In the end, the speed of light teaches us that limits are not signs of weakness in our understanding. They are signs of depth. The universe is not infinitely flexible. It has structure. That structure includes a maximum speed, a causal order, and a geometry that ties space and time together. Light exposes this structure more clearly than anything else. When light travels, it is not just moving through space. It is tracing the boundaries of what can happen. Every photon carries with it the rules of causality, the limits of information, and the shape of space-time itself. Understanding the speed of light is therefore not about understanding light alone. It is about understanding why the universe is the way it is, and why it could not be otherwise. When we say that observation changes how light behaves at the quantum level, we are not suggesting anything mystical or psychological. There is no implication that human consciousness controls reality, or that nature waits to see if it is being watched. What changes is not light's nature, but the physical situation in which light exists. Richard Feynman was very careful about this point, because misunderstanding it leads to some of the deepest confusions in modern physics. Observation, in physics, does not mean looking. It means interaction, and interaction always has consequences. At the quantum level, light does not exist as a tiny object with definite properties waiting to be revealed. It exists as a set of possibilities described by probability amplitudes. These amplitudes spread out, interfere, and evolve according to precise mathematical rules. As long as light is not interacting strongly with anything, these possibilities remain intact. When an interaction occurs, such as absorption by a detector or scattering by matter, the situation changes fundamentally. The range of possibilities collapses into a specific outcome. This is what people loosely call the effect of observation. Feynman emphasized that this collapse is not a mysterious extra rule added to physics. It is a natural consequence of how quantum systems interact with large, complex environments. A detector is not a passive eye. It is a physical system made of enormous numbers of particles. When light interacts with it, the interaction spreads rapidly through the detector and into the surrounding environment. The delicate quantum superpositions that existed before cannot survive this process. They are destroyed not by awareness, but by entanglement. The double-slit experiment provides the clearest illustration of this principle. When light passes through two slits, and no attempt is made to determine which slit it goes through, an interference pattern appears. This pattern is the signature of multiple possibilities interfering with one another. The photon behaves as if it passes through both slits at once, not because it physically splits, but because the probability amplitudes associated with both paths remain coherent. When a device is placed at the slits to determine which path the photon takes, the interference pattern disappears. This is often described as observation changing behavior. What actually happens is that the measuring device interacts with the photon in such a way that the two path possibilities become distinguishable. Once that happens, the amplitudes can no longer interfere. The pattern vanishes. The change is not caused by knowledge gained, but by physical interaction introduced. Feynman stressed that it is the possibility of obtaining which path information that matters, not whether anyone actually looks at the data. Even if the information is recorded and never examined, interference is lost. This makes it clear that consciousness plays no role. Physics does not care whether humans are paying attention. It cares only about interactions that leave traces in the environment. This insight reshapes how we think about reality. In classical physics, objects are assumed to have definite properties at all times. Measurement merely reveals those properties. In quantum physics, properties are not always well defined before interaction. Asking which path a photon took when interference is present is not like asking which road a car used. The question itself assumes a classical picture that does not apply. Once the experimental setup forces the question to have an answer, the behavior of the system changes accordingly. This is deeply unsettling because it undermines the idea of a fully objective reality existing independently of all interactions. Instead, quantum physics suggests a reality that is relational. What can be said about a system depends on how it interacts with other systems. Light does not carry a fixed set of properties. It carries a set of potential outcomes, and those outcomes become definite only through interaction. Feynman often warned against taking this too far philosophically. He did not claim that reality is created by observation. He insisted that the laws governing these interactions are objective and precise. The probabilities are real. The outcomes are real. What changes is the applicability of certain descriptions. Wave-like descriptions apply when coherence is preserved. Particle-like descriptions apply when interactions force localization. Both are real, but they apply in different contexts. This framework also explains why quantum behavior is so fragile. Interference effects disappear quickly when systems interact with their environment. This process, known as decoherence, does not require measurement in any special sense. It happens naturally as systems interact with air molecules, radiation, and thermal noise. The reason we do not see quantum superpositions in everyday objects is not because they do not exist, but because they are destroyed almost instantly by environmental interactions. Light, because it interacts relatively weakly, can maintain coherence over long distances. This makes it an ideal system for observing quantum effects. But even light loses its quantum behavior when interactions become strong enough. A rough surface, a dense medium, or a sensitive detector can all force localization and destroy interference. The role of observation also clarifies many apparent paradoxes. Consider delayed choice experiments, where the decision to observe which path light took is made after the photon has already passed the slits. These experiments seem to suggest that the present can influence the past. Feynman's framework dissolves this illusion. The photon does not have a definite path until the entire experimental arrangement, including detectors, is taken into account. There is no need to rewrite history. There was no classical history to begin with. What matters is the total experimental context. Quantum theory does not assign definite properties independent of that context. This does not violate causality or common sense once we abandon the assumption that particles must always behave like classical objects. The confusion arises only when we try to impose classical narratives on quantum events. Feynman was particularly critical of explanations that rely on vague language. He insisted that if a concept cannot be stated clearly in terms of physical interactions and mathematical rules, it should be treated with suspicion. The idea that observation changes reality is only meaningful if observation is defined as interaction. Once that is done, the mystery becomes manageable. This also explains why different types of measurements produce different outcomes. Measuring position destroys momentum information. Measuring momentum destroys position information. This is not a limitation of technology. It is a fundamental feature of quantum systems. The act of interaction that defines one property necessarily disrupts others. Light is not hiding information from us. The information simply does not exist in a definite form until interaction creates it. Feynman often pointed out that this does not mean anything goes. Quantum theory places strict limits on what can happen and with what probability. The uncertainty is not chaos. It is structured uncertainty. The probabilities are not arbitrary. They follow precise rules that have been tested with extraordinary accuracy. The idea that observation changes behavior also has practical consequences. Quantum technologies rely on careful control of interactions. In quantum communication, preserving coherence is essential. Any unwanted interaction with the environment can destroy information. In quantum sensing, deliberate interaction is used to extract information with extreme sensitivity. Understanding how observation affects systems is not a philosophical luxury. It is a technical necessity. This perspective also reframes the meaning of measurement. Measurement is not a special act that sits outside physics. It is just another physical process, governed by the same laws as everything else. Detectors, observers, and instruments are part of the system, not external judges. This eliminates the artificial boundary between observer and observed that plagued early interpretations of quantum mechanics. Feynman's approach was pragmatic. He did not try to answer metaphysical questions about what reality really is, beyond what experiments can test. He focused on what the theory says and how it works. Quantum electrodynamics predicts outcomes with astonishing accuracy. That success matters more than whether the theory fits our intuitions. At a deeper level, this keynote challenges the classical idea of an objective world composed of independent objects with intrinsic properties. Instead, it suggests a world composed of interactions, correlations, and probabilities. Light is not a thing that behaves one way or another depending on who looks at it. It is a participant in a network of interactions, and its behavior reflects that network. This does not diminish reality. It enriches it. The universe is not less real because outcomes depend on interactions. It is more structured. The rules governing these interactions are precise and universal. What changes is our role as observers. We are not passive witnesses. We are physical systems interacting with other physical systems. Feynman often said that quantum mechanics is not strange because it is mysterious, but because it is unfamiliar. The discomfort comes from trying to force new ideas into old frameworks. Once we accept that observation is interaction, and that interaction changes systems, the mystery becomes less threatening. Light teaches this lesson with exceptional clarity. When unobserved, it spreads, interferes, and explores possibilities. When observed, it localizes and delivers energy in discrete packets. Both behaviors are real. Neither is more fundamental than the other. They are complementary aspects of the same underlying process. In the end, the idea that observation changes how light behaves is not a statement about human importance. It is a statement about physical interaction. The universe does not care whether we are watching. It cares about what is interacting with what. Light responds to interaction because interaction is what defines events. Without interaction, there are only possibilities. With interaction, there are outcomes. This keynote reveals a universe that is not built from static objects, but from dynamic processes. Reality is not a stage on which things happen independently. It is a web of interactions in which outcomes emerge. Light, through its sensitivity to observation, exposes this structure more clearly than almost anything else. It shows us that to understand the universe, we must stop asking what things are doing in isolation and start asking how they interact.